Hello and welcome back to GCSE Science Simplified, the podcast that takes GCSE physics and makes it actually make sense. Today we're talking about magnets, why some stick, why some don't, why compasses point north, and why magnets seem to work even when nothing is touching. Magnets might feel like magic, but by the end of this episode you'll see they're just physics you can't see. Let's start with the rule that never changes. Opposite poles attract, like poles repel. If you push two north poles together, they push apart. North and south, they snap together. You've probably felt that invisible force fighting you when you try to force magnets together the wrong way, or opening the fridge door getting a snack. That push or pull works even with a gap between the magnets. No contact needed. That's your first clue that something invisible is going on. This is defined as a non-contact force. Now here's something important for exams. Not all metals are magnetic. Iron, steel, cobalt and nickel are magnetic. Aluminium, copper, not magnetic at all. Let's talk about permanent and temporary magnets. A permanent magnet, like a fridge magnet, stays magnetic all the time. Alloys of iron are often used for these because they keep their magnetism. You've probably played with neodymium magnets at home. A temporary magnet is different. Iron, for example, becomes magnetic only when it's near a magnet. Take the magnet away and the iron quickly loses its magnetism. This happens because iron is classed as a soft magnetic material. Because its magnetic domains, think of these like little magnetic arrows pointing different directions in the iron itself, these domains can easily align with a magnetic field and just as easily lose that alignment when the field is removed, making it temporary and responsive. This type of magnetism is called induced magnetism. The magnet hasn't magically changed the iron forever, it's only affected it while it's nearby. Importantly, with induced magnetism, you can only have the force of attraction. It never actually repels. So, what's actually causing these pushes and pulls? The answer is the magnetic field. Every magnet has a magnetic field around it, an invisible region where magnetic forces act. We use field lines as a model to represent this. The lines always go from north to south, and the closer the lines are, the stronger the field. That's why magnets are strongest at their poles. Field lines aren't real objects, they're a scientific model that helps us visualize something invisible. You've probably drawn them. It looks like a butterfly or a burger, depending on what you're into. In the lab, we use plotting compasses to map magnetic fields. Each tiny compass aligns with the field at that point. Move the compass around a bar magnet and draw arrows. You'll start to see the full field shape appear. This same method works for the Earth's magnetic field too. Compasses don't point north because of magic. They align with the Earth's magnetic field. So here's the big question. Why does Earth have a magnetic field at all? We can't drill down to the core, but we can use evidence. Compasses work everywhere on Earth. That tells us our planet must behave like a giant magnet. The best explanation is that Earth's core contains magnetic materials, like iron, moving in a way that generates a magnetic field. This is a powerful example of science using models and evidence to explain something we can't directly observe. So remember, magnets push and pull because of magnetic fields. Some materials are magnetic, others aren't. Some magnets last forever, others only work temporarily. And every time a compass points north, it's reminding you that Earth itself is a magnet. That's magnets and magnetic fields. This has been GCSE Science Simplified. See you next time.